So since we are doing these statistical tests in order to prove that there is a significant differential gene expression, but these p-values, they tell us about the reliability of our results, or they just give us some confidence numbers or confidence measures. We may be right, but sometimes we may be wrong because it's just our assumption. So we are taking those p-values under a curve, and there is the probability that those differences are not significant, but actually they are there by chance. So we may be wrong depending upon what is our alpha level. We call it as alpha. For example, here if we say that any measure or any value which is there in top 5%, that top 5% we call it as alpha. So we may be wrong 5% of the time, because if there is a curve, there are some 5% value in its tail. So we are declaring by ourselves that those values are significant, but we may be wrong 5% of the times. So how much of the truly changed genes we detect without sacrificing the specificity? We call it as sensitivity. Specificity is we are incorrectly thinking that the gene expression is altered. So actually we are thinking that the expression is changed, but actually it's not. So we call the first one as type 1 error, alpha, or the p-value, where we can have a false positive. We declare a gene to be a significant, but it may be a false. So positive in a sense that it is significant. We came up with a number, a differentially expressed gene, but we might have reported a wrong gene. There is another measure, we call it as type 2 error or false negative. So sometimes we reject some null hypothesis, but that null hypothesis may be true. So we are kind of, here these two measures are correlated with one another. Higher the one, the lower is the other. So let's look into this overall process in this chart. So we have a null hypothesis, and this null hypothesis may be correct, this column over here, or it may be wrong. So this is our decision. So we are rejecting an H0. H0 was correct, null hypothesis was correct, but we rejected that. We accepted the alternative hypothesis. So actually there was not any significant difference, but we detected a difference. So in that case we are doing an error. We call it as type 1 error or alpha. So for example, we are declaring anything which is significant if it is present in top 5%, but at the same time we may be wrong 5% of the times, because 5% of the values will be there in the upper tail in that particular 5% area of that tail. So in that case we do this as alpha or type 1 error, and 1 minus alpha is opposite. So here alpha and here is 1 minus alpha. So there is null hypothesis which was correct, and we accepted that null hypothesis. So in that case the probability of this thing is 1 minus alpha, so which is, in this case, we did a correct thing. In second scenario, we have a wrong null hypothesis and we rejected that. So in that case we did a correct thing. So that thing is, we call it as 1 minus beta. But this null hypothesis was wrong and we accepted that. So in that case we did an error which we call it as type 2 error or beta. So here it's beta, here it's 1 minus beta. So the power of a statistical test is this thing. You reject a null hypothesis which is a wrong one. So that thing is called as your power, 1 minus beta. So most of your test we want a good power. This graph is called as ROC or receiver operator characteristic curve. On one side we have true positives, true positive rate on y-axis. On the x-axis we have false positive rates. True positives are actually those genes which are actually differentially expressed and then they are detected, whereas the false positives are, in true sense, they are not differentially expressed, but even then they are detected as these differentially expressed genes. So they are kind of, your false results, they are false positives. So what we expect this curve to look like? In order to have an excellent result, you should have this yellow line. So you should have more true positives as compared to your false positives. In good results, the curve is like this, where this one is worthless or bad result, where you have equally true positive rate as compared to false positive rate. So this is how we do these tests in real life. So we have gene 1, wild type 1, 2 and 3 versus mutant 1, 2 and 3. If we throw it as an unpaired t-test, remember guys, Excel gives us the p-values over here. The p-value is 0.00. In a paired, again it's 0.00. So this p-value is less than alpha, less than 0.05. So there is a significant difference of expression between these three replicates within the wild type. So this is one distribution for this gene G1 and versus these mutants. So mutants has, as you see, the expression is higher in mutants versus it's low in these wild types. So it takes their mean for these three here, compare them and come up with a p-value. Same way there is another gene, gene 6. So again the p-value is 0.12. If you do it as unpaired test, which is non-significant, here it is significant. And then we have at random we have picked up these different genes. So we have G1, G6, G4 and so on. So the point of putting this thing in this slide over here is we have to do these multiple tests, all of them at once. So there is a probability that this test may be wrong. So that is our alpha, which is 5%. And again this test may be wrong 5%. So how many tests you are throwing, your error rate or your alpha will be increased. So multiplicity issue, this we call it as multiplicity issue, is where you have multiple testing. So it occurs when the chance of any one of the results being called significant, while in reality it is not, is small, but since many tests are performed altogether, guaranteed that many of the results will be incorrect. So many of the false positive results will be there if you are throwing so many tests altogether. We have expression studies which pose unique statistical challenges due to interrogations of so many genes simultaneously, and this leads to what we call it as multiple testing problem or multiplicity issue. So for example, at alpha is equal to 0.05, out of 100, 5 tests may be wrong. How many tests may be wrong? If you are doing 20,000 tests, so the probability is 0.05 or 5%. So 5% of 20,000 means 1,000 tests will be expected to be wrong. So there may be 1,000 false positives in your results. So there are different methods to correct for this issue. One of them is called as Bioinformatics correction. So it is that set the alpha equal to alpha by number of tests. So if you are throwing, for example, 20,000 tests, so rather than looking into a gene to be a significant, if its p-value to be 0.05, rather than that, look into 0.05 divided by 20,000. In that case, a gene is significant if its p-value is less than 2.5 into 10 power minus 6. There is another approach to correct for this multiplicity issue, so that we call it as false discovery rate. So sometimes it's okay that we let some false positives to be there. So rather than using the p-value, they use another opposite to it, we call it as Q. So in that case, the Q is what we call over here as false discovery rate. So the expected proportion of false positive among the positive results. So let's have Q is equal to 0.05. If you call 1,000 genes significantly changed, 50 amongst them might be false positive, but the rest of them will be then false, will be true positive. So multiple testing problem arises if you are throwing so many tests together, and there are different approaches to correct for this issue.